previous lecture, we talked about the diffusion force, which sets up the concentration gradient, and the electrical force, which sets up the voltage gradient. These two forces are at work. They're kind of given to us by the universe for free. It's kind of like gravity. They're just there, and they have these effects. We don't necessarily understand why they're there, where they come from. But the two forces are constantly trying to push these ions in or out of the cell. But that impermeable cell membrane is preventing that movement from happening. So there's energy already available to make these ions move, but the impermeable membrane is preventing that from happening. As such, the impermeable membrane stores potential energy. It's potential energy because if you just put a hole in the membrane, then boom, ions are going to shoot through that hole. Well, you can do that by inserting those ion channels into the membrane and opening those channels at select times. By inserting those channels, that potential energy is released by the opening of the ion channels. Now let's talk about electrical potentials. So, electrical potentials. A potential refers to a difference. Okay, you could think about one's potential to become an astronaut. The potential is the difference between being an astronaut and where they are at that current point in time. They've got the potential to become an astronaut if they expend energy in these particular ways. So, potential energy. And of course, electricity is a form of energy. So we can talk about electrical potentials. Difference in electrical charge between two locations, say the inside and the outside of the neuron. As such, this is a potential or a difference across the membrane. So we can refer to it as a membrane potential. The membrane maintains a differential charge. That is, because the membrane is impermeable to these ions, the charge that is outside of the cell stays outside of the cell, and the charge that is inside of the cell stays on the inside. And as such, the neuron is typically negatively charged relative to the inside. That is, when the neuron is at rest. That is, it's not firing. We call it a resting potential. And a resting potential is the potential difference between the inside and outside of a neuron that is at rest. So we just have the impermeable membrane. Yes, we have ion channels embedded in that impermeable membrane, but those ion channels are closed during rest. At least most of them are closed during rest. Therefore, the negative charge inside is maintained, and that's negative charge relative to the outside, which is relatively positively charged. Now, if we open those ion channels and we release that potential energy into kinetic energy, we're going to get movement of ions in and out of the cell through these ion channels. That's when the neuron is in action. Hence, we call it an action potential. An action potential is the potential difference between the inside and outside of the neuron when it is in action. Okay. The difference in charge between the inside and the outside of a neuron when it's in action. The action potential. So now let's understand how is it that we can record this resting potential and this action potential. We'll discuss how we record it, and we'll show what it looks like on the screen to see one of these action potentials occur. Now let's discuss how we record action potentials and resting potentials and so forth in the neuron. This is done through a technology that uses a glass pipette. Glass pipettes are, pipette is French for small pipe. So these are tiny tubes that are made to penetrate the cell membrane without destroying the cell membrane. So if you look at the photograph on the left, coming in from the right side of that image, we can see the electrode. And really what we're seeing here is the glass pipette. The electrode is inserted inside that glass pipette, but the electrode itself does not penetrate the neuron, just the glass does. And this is because the glass can be fashioned to a fine enough point that it can puncture that cell membrane without damaging the cell membrane. And at the very end of that glass pipette, if we look at this image on the right, we see the glass pipette magnified, and we can see that there's a tiny hole in the end of that pipette, and that hole allows the fluid inside the neuron to diffuse into the glass pipette itself. That fluid from the inside of the cell, when it's at rest, is negative 65 millivolts. It has a negative charge to it. The fluid enters the glass pipette at negative 65 millivolts of charge, and that fluid makes contact with the electrode that is embedded inside that glass pipette. Now we take that electrical current that we recorded from the inside of the neuron, and we display it on what's called an oscilloscope. At least that's what it was in the old days. Effectively, we were just using computer screens to plot the electrical signal from the inside or the outside of the neuron. If we look at the right side, the upper right side of this image, we see the typical display of an action potential. We see that the neuron is at about negative 65 millivolts, and then it fires an action potential causing it to go up to just about positive 40 millivolts. And then it's going to drop back down and return to resting baseline of negative 65 millivolts. This is all made possible by the glass pipette allowing the electrical fluid into the pipette and making contact with the electrode. Now that we understand how the resting potential and the action potential are recorded in neurons using a glass pipette, we can explore the nature of the action potential in terms of what it looks like through the electrical current coming through this electrode inserted in the glass pipette. So if we were to insert a glass pipette into a neuron, the signal would immediately read negative 65 millivolts, which is the resting potential of the neuron. By the way, you will sometimes hear from other sources that the resting potential is negative 70, and that can be true as well. There's 100 billion or so neurons in the brain, and each has, maybe not each, but some have different resting potentials than others. For our purposes, we'll go with negative 65 millivolts, but if you ever read or hear negative 70 millivolts, don't be troubled by that. So the electrode would read negative 65 millivolts at resting potential. And if we were to depolarize the neuron, in this case, depolarizing means to move closer to 0 millivolts. If we depolarize the neuron from negative 65 millivolts to negative 55 millivolts, we will have hit excitation threshold. Excitation threshold. This is a value, negative 55 millivolts, at which sodium channels in the cell membrane will open up. These sodium channels opening up will allow sodium to follow its concentration and its voltage gradient to the inside of the cell. It'll be going from the outside of the cell to the inside of the cell. This causes the inside of the cell to become more positive. pull out my laser here and see if I can get that to help me. Hopefully you'll be able to see this. We've reached excitation threshold. The sodium channels have opened up. Sodium that is concentrated outside of the cell will follow its concentration and its voltage gradients to the inside of the cell and cause the inside of the cell to become more positively charged. This is called the rising phase of the action potential. This rising phase continues until the neuron reaches around positive 40 millivolts. This is referred to as the overshoot. It shoots over 0 millivolts up to almost positive 40. So this has been rapid depolarization of the neuron, creating this rising phase. Now we'll get the rapid kind of repolarization or hyperpolarization, whereby the sodium channels at this stage of the action potential have begun to close so that positive charge stops running into the cell. And also at this time, potassium channels are going to open. Potassium is concentrated inside the cell. So if you open potassium channels, potassium will follow its concentration gradient to the outside of the cell. This means that positive charge is leaving the cell. If positive charge is leaving the cell, that means the inside of the cell is going to become more negatively charged. So we stopped letting sodium in, and we've begun letting potassium out. The inside of the cell returns to a negative state. It will actually undershoot. It will actually go below negative 65 millivolts, but then come back to rest at that resting potential of negative 65 millivolts. That is the action potential. Starting at rest, we depolarize the neuron to excitation threshold. That causes the opening of sodium channels. Sodium rushes into the cell, giving us the rising phase of the action potential. We cap out at close to positive 40 millivolts by closing the sodium channels and then opening the potassium channels. Now potassium rushes out of the cell. Positive charge rushing out of the cell makes the inside of the cell become more negative. It continues to go negative to where it undershoots beneath the resting potential, but then returns. That's what an action potential looks like on an oscilloscope. But now let's take a look at what the action potential looks like in the cell membrane as far as the ions and the ion channels go. We're making use again of the concentration and the voltage gradients to explain the movement of sodium and potassium for now in and out of the cell. This information is available on the learning management system, a file called resting membrane potential video. And what I'm going to do is explain what's going on in the video, and you can separately then download and watch in the VLC media player. That's what you'll need to actually see and hear the video. If you use a different media player, you're probably just going to hear the audio but not see the video. So make sure you use VLC media player to play those videos, but you can separately watch them and kind of bounce back and forth between my explanation of what's going on and the video itself. So we are going to refer to sodium and potassium mostly. We'll talk briefly about chloride here. But the first thing we want to notice is that we have the phospholipid bilayer, that cell membrane running from one side to the other of the video screen. And inserted in that cell membrane ever so often are sodium channels and potassium channels. we'll talk also about a sodium-potassium pump. That'll come in a little bit. For now, let's talk about the relative concentrations and voltages of ions inside versus outside of the neuron. To begin with, let's talk about sodium. Sodium has a positive charge, so its voltage gradient is trying to pull it to the inside of the neuron. Its voltage gradient, that is indicated here by a red arrow. Of course, it can't go across the cell membrane, not at this location, because there's not a sodium channel. But for now, the idea is the voltage gradient is pushing it to the inside of the cell. And then in black, we also have the concentration gradient pushing sodium to the inside of the cell. Now, the relative concentration of sodium is on the outside of the cell, and that is represented by the larger rectangular box here. If we look at sodium, the sodium rectangle in the inside of the cell, it's smaller, and that's representing the idea that there are fewer sodium ions inside than there are outside the cell. That explains why the concentration gradient is pushing toward the inside of the cell. And the inside of the cell has a negative charge, which explains why the voltage gradient is also pushing toward the inside of the cell. Now, they can work that way, but in concert with one another, pushing in the same direction, but they can also work opposite one another. If we take chloride, yes, it has a higher concentration outside the cell than inside the cell, which means the concentration gradient, the black arrow, is pushing chloride to the inside of the cell. However, because chloride is negatively charged and the inside of the cell is negatively charged, chloride's voltage gradient is actually pushing it outside the cell. We see this kind of contrary gradient with potassium as well. It's concentrated inside the cell relative to outside the cell. So its concentration gradient is trying to push it out of the cell. However, because potassium is positively charged and the inside of the cell is negatively charged, the voltage gradient is trying to push potassium into the cell. Now, there are also these other negatively charged anions that are trying to be pushed outside the cell, but there are no channels or other method by which they can get through the cell membrane, so they always stay here. And again, most of the time, the inside of the cell is negatively charged at around negative 65 millivolts. But if we open these channels, then sodium is going to follow its concentration and its voltage gradient outside the cell, and potassium is going to follow, it's going to go against its voltage gradient, but it's going to follow its concentration gradient from the inside to the outside of the cell. Now, this happens in a few of the sodium and a few of the potassium channels. Most of the channels at resting membrane potential are closed, as we see here. But there are a few that are open, creating leakage. We've got some sodium at rest leaking into the cell and some potassium leaking out. And we need to correct for that. It's leakage that we don't want, we want to correct for it. That's where the sodium-potassium pump comes in. The sodium-potassium pump takes sodium that has leaked in along its concentration and its voltage gradient to the inside of the cell. We want to take that sodium and use the pump to push it back against its concentration and voltage gradient. Push against those gradients, requiring energy to put the sodium back to the outside of the cell. And the potassium that is leaked out, we want to push back against its concentration gradient, requiring energy, into the inside of the cell. So the sodium-potassium pump is using energy to compensate for the leakage of sodium inside the cell and potassium out of the cell. And so all of this is taken to explain just what the neuron is doing when it's not doing anything. Next slide will talk about what is the neuron doing when it's in action. The next video to which we'll be referring is labeled Action Potential Video in the course shell. This video describes the opening and closing of the sodium and potassium channels during an action potential. If you recall from a previous slide where we looked at the tracing on the oscilloscope, we saw that the neuron at rest is at negative 65 millivolts, that if we depolarize it to excitation threshold at negative 55 millivolts, we will get a rising phase of the action potential. And then that is followed by the falling phase of the action potential. Well, the rising phase of the action potential is due to the opening of these sodium channels, colored yellow in this video. And the falling phase of the action potential is due to the opening of potassium channels during the falling phase of the action potential. So here we see an electrode with a glass pipette inserted into the neuron, and the video doesn't really show this, but you're to imagine that there's an oscilloscope there reading about negative 65 millivolts. And then the video will show, through a red color, it will show an influx of positive charge, that is depolarization. And when enough positive charge comes in to bring the neuron from negative 65 millivolts to negative 55 millivolts, that reaches the excitation threshold of these sodium channels. Positive voltage, again, comes into the neuron, brings these sodium channels from negative 65 millivolts to negative 55 millivolts. It causes those channels to open. Now that those channels are open, sodium out here outside the neuron is going to follow its concentration and its voltage gradients to the inside of the neuron. That will make the inside of the neuron become positively charged. That is the rising phase of our action potential. Once that rising phase of the action potential has reached about 40 millivolts, positive 40 millivolts, then that causes the sodium channels to close and the potassium channels to open. Now potassium is going to leave the cell. Yes, that might seem ironic that you're going to make the inside of the neuron become more negative by moving a positively charged ion, but the point is that positively charged ion is leaving the cell. So positive charge leaving the cell makes the inside of the cell more negative. That's why opening potassium channels creates the falling phase of the action potential. Opening those potassium channels causes potassium to follow its concentration gradient to the outside of the neuron. Potassium leaving the cell makes the inside of the cell become more negatively charged.